So hello, I am Leonardo Simbaum, and my study was about the analysis of the impact of the part air cooling on the interlayer yield strength in the additive manufacturing of PLA and PETG. So basic concept overview. This one is the extrusion cooler. It blows air between these ducts dielectrically at the extruder, and this slicer that I utilized is the simplified 3SD. The materials, as the title suggests, was PLA and PETG. I utilized PLA from two suppliers, 3D fila and Slant SD, and PETG only for 3D fila. So, Bellehumer said that the longer a material remains above the glass transition temperature in the 3D print, the smaller the resulting void spaces will be. Void spaces being just blank spaces between two print lines. And as Sun said, the bottom layers where the part is hotter for more time, the void spaces are smaller. Why that is important? It's because the greater these void volumes, the smaller is the useful section of the part that can distribute the forces applied to it. So it will you will have a lower yield and rupture point strength. Here are the parameters utilized. It was a layer height of 0.2 millimeters, a printer temperature of 250 to PETG and 210 to PLA, and a printing speed of 60 millimeters. The part was solid, utilizing the base layer. So here was how I defined the parameters, utilizing a temperature tower to check and define the ideal temperature, and a test cube to see if there will be any under extrusion or any other problem. So if I set an infill to 100% at simplified SD, the part is not solid. You can see here that there is a lot of gaps. So how do you print a solid part? Well, you put a number of base layers higher than the entire part. The test specimen I made was according to the ISTM D638, and it has a height of, the type 1 specimen has a height of around 825 layers. So with 999 base layers, I print the entire part as a solid base. And here are the results for the 3D fila PLA, where we can see that the parts manufactured printed vertically, and with the turning fan turned off and on at the maximum, there was a reduction of around 37% on the yield and rupture stresses. And for the ones printed horizontally, the difference between the cooling fan turned off and on at the maximum was around 80.5% yield reduction on the yield and rupture. From these two tests, the yield and the rupture points were the same, and so the part where the part reaches the yield point, it rupture. We can also see here that I choose to test this region a little bit more, and it is because the most interesting tests where the drop really happens and then stabilizing here. And for the ones printed horizontally, as the reduction is quite small, I choose to just test it with the cooling fan turned off and on maximum. For the elongation, there was no difference between them. The ones printed vertically broke in the layer lines, and the ones printed horizontally broke clear and without any elongation. The results for the splinters DPLA were quite similarly, with a reduction for the ones printed vertically between the cooling fan turned off and on at a maximum of around 45%. We can see that the drop happened a little bit quicker here, but the range of values is around the same. And again, the yield and rupture point happened at the same point. For the ones printed horizontally, with the cooling fan turned off, the reduction was around 8.2% on the yield stresses, but it had a different point for the rupture stresses, as we can see here, a little bit lower. So it starts to deform and form a neck, then rupture. And for the ones manufactured with the cooling frontal node at maximum, it was the same thing. It broke at the same point. Here we can see the elongation. The ones printed vertically broke in the layer lines, and the ones manufactured horizontally, we cannot really see, but the one with the cooling frontal node off, there's a little bit of a neck forming here. It's really quite not possible to measure it, basically. And for PET G, we can see here for the ones printed vertically and horizontally that there is a different behavior. The difference in the yield and rupture stress points for the ones manufactured the cooling frontal off and on at the maximum was at around a 39% reduction, with the turning frontal off being the most resistance one, and the dropping a little bit more linear here. And for the ones printed horizontally, the yield stress reduction was about a 13% drop between the current frontal off and on the maximum. And for the rupture strength, here the behaviors really change. You can see that this one is quite below because most of the test specimens did not even rupture here. And here they rupture after forming the neck. So the ones printed vertically broke in the layer lines, same as the other materials, but the one printed horizontally, with the turning fan turned off, it formed the neck and it was spreading through the print until it reaches the limit of the test machine. And the one printed horizontally, you can see that it formed the neck, and when it would start to spread, it ruptured. Here we can see the elongation test results for the stress strain diagram. The one turned off, we can see that it reaches the yield point, it drops the tension, forming the neck, and when the neck starts to spread, basically, it stabilizes. As for the one with the cooling fan turned on at maximum, we see that it reaches that yield point, forms the neck, and when it starts to spread, it breaks. And then we can say that the one manufactured with the cooling fan turned off behave as the classic stress diagram for semi-crystalline polymers. The conclusion then are that there was a reduction of 40% between the cooling fan turned on and off and at maximum for the parts in the yield strain and ruptures, and of around 90% for the parts manufactured horizontally. There was not really a difference between the elongations between the tests, and these both manufacturers behaved really similarly. As to PET-G, there was a reduction of around 39% between the cooling fan turned off and on at maximum speed for the yield and rupture strain. And to the ones manufactured horizontally, the reduction was between around 13%. The parts manufactured horizontal also had a really significant change in behavior, even behaving like the classic stress diagram for semi-crystalline polymers, not really rupturing, but forming the neck and elongating past the whole part. So the difference between the yield strength for the specimens made horizontally and vertically with the cooling fan turned off was between 12 and 32% of the yield strength, meaning that printing a part with their layer lines perpendicular to the force, it's really more, it's stronger, even if the cooling fan turned off, around 12 to 30%. And if we use the cooling fan at 100%, the difference between the horizontal and vertical ones is even higher, being around 40 and 55% of the yield strength, just by changing the layer orientation. So it shows that to achieve the better mechanical properties, it is necessary to consider the printing direction, leaving print layers perpendicular to the force applies, and turning off the cooling fan will provide better mechanical strength and even allow to greater stress under tensions in the case of the PET-G. Thank you all, and I hope you enjoy.